All right, and welcome to another episode of Makers on Tap, the first episode where the intro music didn't screw up in about 6 months.
Woo!
It's a good omen. It must be a Bones Day. I'm so jazzed.
Hell yeah.
Today with us, I'm your host, Joe, and who else is with us?
Chris.
And Sanjay. I'm not a host.
I'm so jazzed to have Sanjay back with us again. And unfortunately, we don't have a lot of time to sit and ramble like we have in the past, but I'm sure
I'll
we
just
will
take
get
over
off
hosting
topic.
after you. And we'll just...
That could work. That could totally work.
The Sanjay only podcast. We're going to just have you just ranting about movies, podcasts, just whatever you want.
Man, that'd be an interesting one. You should do that. I'll help you set it up. It'll be good. We can do it as an offshoot if you want. You just moved your shoulder. What is that machine behind you?
That is the first ever Mendel 90 that
I wondered.
So this is horrible. Or it was even horribler. It used to have anodized aluminium tube as linear shafting.
Nice. Did it have roller bearings like LMUU bearings, or did it have sleeves? Oh God!
It was very loud. It was very loud. But it has some nice features like a die-bond bed. Mendel 90s, nice machines.
That's amazing. I really wish I still had my first Prusa Mendel. I tried to buy it back from the kid I sold it to a bunch of years ago, and he had already stripped it down for parts. Yeah. One day. But yeah, so what have you been up to? You've done a lot of interviews lately, so I don't want to rehash those. But in the last few weeks, you guys have launched Revo. You've teased a tiny Hemera. You've teased some new nozzles that are just like baller, and I can't wait to see. Yeah. I've beta tested Revo in like all of its revisions, and I love it. It's on that machine and that machine, and those are the only two that I currently have it on right now. So
that's what printed most of the parts for the thing I'm making, right?
Yeah.
It's insane.
They printed all of the milk crate parts, all of the revisions of the prototypes. Yeah.
Trooper.
Yeah.
What have we been up to? In the round, there's been like this big kind of COVID constipation of things that have been in development for quite some time, and somehow, despite best efforts, they all seem to be ready all at once. So
fair.
Yeah, like Revo validation finished just in time for TCT, for us to be 100% that those last few bugs were ironed out. You're probably aware of those ones.
That
was a tough nut to crack.
I mean, but that's what we do, right? Like we work on it, and then there's like, oh well, here's this deadline, so let's just get it. It's finally that last push, and
to the point where I was like burning the candle at both ends. Like I had to take like a week and a half off just to like after TC just like crash, and like
well deserved.
Yeah.
But yeah, that got done. Obsidian has just passed all of its final validation, I think. There's some like coatings are hard.
Both figuratively and literally.
That unintentional, but but there's a lot of deep magic in there, and like just things that to us were unknown unknowns. But I'm glad it failed here in the testing program, because they would have sucked to.
Again, it's what we do.
Yeah. There's a whole other product. Oh yeah, no, that one we're not talking about yet.
I want to hear about that offline.
Yeah, yeah.
So I
Okay,
guess
yeah.
like the first thing. So the V6 came out in what, 2013,
14, 13?
14,
Don't quite
somewhere in
remember.
there.
Around there.
So how long have you guys been working on Revo, like since the span? Like when did you go, okay, we have this new idea, we want to kick this off? When did you guys start working on Revo?
That's a very blurry thing. I guess the longest lead tech was the develop our own heater and sensor manufacturing and assembly capability in house.
Mm-hmm.
And that is still, I think, that's the most technically complex part of the system. I guess if you look at Revo and a Revo heater, like you could design that in like 5 minutes with a Sharpie, right? It's just like you've got like the filament is round, so you make a round hole, and then you have to get the hot into it, and so you may have put a hot maker, and so a circular hot maker goes around the round hole, and oh, I have to do a sensor somewhere in here, and we'll find somewhere to shove that in.
Mm-hmm.
That is not exactly the most like difficult CAD. You look at a Revo heater;
Yeah.
it's just it's a ring, right?
Yeah, it's intuitive design.
But one extreme of industry to look at perhaps is automotive. In automotive, you don't so much design products. The main thing that you're designing or the innovation is in the manufacturing process.
Mm-hmm.
And V6 was very much a product design exercise within the constraints of manufacturing that other people did. And as we mature and scale and have to compete on price and quality and things like that, that are part and parcel with manufacturing, then we kind of have to, the amount of product design gets like slightly trimmed down, and the amount of manufacturing engineering comes in, and that'll be a creeping thing, as it is in all maturing industries. I
I,
mean, look at a Dreamliner looks pretty similar to McDonnell Douglas DC, like 1, 2, like the numbers, the ones. Like they're
Yep.
not changed. They look the same. But materials and manufacturing have changed. They're just unrecognizable from back then,
right.
and that's really what's driving the improvements in like range, sustainability, passenger comfort, and the like. And for us, as we exhaust design optimization, which is an easy and cheap target, then one bumps into the fundamentals of what the process and the constraints of that process. So you start bumping up against that. And with V6, a lot of changes did happen to V6, and we optimized it, and there was a lot of like tweaking. It's kind of a moving target.
Absolutely.
Mm-hmm.
And we even changed the manufacturing process quite significantly. But you get into this, like, you just reach a natural point where like progression and making big advances is just no longer, you have this like mutual interdependent constraint thing going on.
So like that's it's an interesting point. We talked about this in the past, just you and I, but like you kind of hit a point where you like outdesigned V6 and you're no longer designing around commodity materials, and the industry has gotten to the point now where we could design around needs instead of commodities. And
Yes,
that's where Revo went, right?
exactly. And so I guess the need is for an extrusion system that isn't painful to the user.
Right.
And back when, it was very enthusiastic folk with a great deal of mechanical experience, the amount of pain caused by the need for, using multiple tools and dealing
Mm-hmm.
with hot parts is kind of lower because there are a whole smorgasbord of other things that are horrible.
Right.
But as
Yeah.
those horribles diminish and we introduce things like auto bed leveling and slices that are really well like tuned and tweaked, and the user interface and experience there has improved. We just felt like the biggest we felt like extrusion systems were, I don't know, bias is very like extrusion system centric and will be,
Mm-hmm.
that's us. But we felt like the usability and user experience of extrusion systems was kind of one of the big things that still kind of sucked.
Yeah. You guys took a lot of feedback. Like I said, I was part of basically every version of this beta, and it was really interesting to see how you broke down the different design characteristics of the extrusion system. Every beta had a subtle tweak to a specific part of the hot end. There were several rounds,
Yeah.
and you were really diligent about taking user feedback on those specific things. And every revision, you could see thoughtful iteration into those things and like see design changes that mattered. And my favorite part was you brought back groove mount, even though you hate it so much. You brought back groove mount because the beta rounds cried for it. There were so many of us, me included, who like our only negative feedback was I don't have any way to mount this stupid thing to my mass of existing extrusion systems,
Yeah.
and uh, give me back groove mount at least for an option. You know.
Yeah. And so groove mount is only present in the kind of V6 compatibility layer version
Right.
of the
Yeah.
system.
Exactly.
But there is no Revo Micro, which is the more optimized, smaller heatsink with groove mount on it.
Yeah. Yeah. But I love the idea of being able to drop in the new technology into the hundreds of thousands of existing printers so that we can experience things like quick change and all the great things that come from that, because being able to drop in a new nozzle instantly, it's a complete game changer. It they completely changed how I designed parts, how I looked at my processes, how I stacked up my prints. Yeah, it was fantastic.
And yeah, I think that's the thing that we were targeting from the very, very start is that fundamental shift in user behavior towards the printer and extrusion system, right from the I see a problem and now I'm in kind of like that design, solve,
Hmm.
manufacture loop, and I'm kind of implicitly thinking about resolution and nozzle size and things like that because there are very large gains to be had.
Yeah.
If you can design your part around a zero point 0.6 over a zero point 0.4, you can actually barely tell visually a lot of the time, I find.
Hmm.
Um, but your print times are halved,
Right.
if
Yeah.
not
Yeah.
better.
Yeah.
What
Because you
was
have to remember
interesting.
that going from a zero point 0.4 to a zero point 0.6 is an unintuitively large leap because it's a square factor of
Yeah.
yeah. Um, There's lots of intricacies in that, but I mean, fundamentally, geometrically, there is a square factor change. So
Yeah, and that all comes down to flow rate and push rates and like melt factors. And it was interesting during COVID. One of the other tool changer beta testers, Brendan and I, spent a lot of time trying to figure out how to treat zero point 0.4 nozzles like 0.6 nozzles, so we didn't have to do nozzle changes, but we could crank out visors faster.
yeah,
And like it works, sort of. It's not as good as a 0.6, but it does work.
yeah, and I think there's a lot to be learned from that as well. There's still a lot more work to be done in nozzle geometry optimization, because diameter isn't the whole story. That
Right,
really
yeah.
gets into a can of worms. With Revo, we've preserved that which was extant on V6 because it means that you can transition to Revo and not make any changes to your slicer profiles at all, and you'll end up with a system that prints the
Hmm.
same, if not more gooder, and you will have quick changing capability.
And for the most part, no changes to firmware. One of the things that was asked of me a lot when we were finally able to talk about the beta was, with the rapid heat up times, did I have to redo PID tunes? And I, for the large part, didn't. I did on one machine because somebody asked me to see what it would do to my heat up times, and they didn't change at all. And
Yeah, you can tune in a bit more stability into your loop, but
right,
the
yeah.
thing is, it's just so absurdly responsive and has such little like. It's not just your ability to crank the gradient up; it's also the dead time and
Hmm.
lag between input response. So these things like combine to give you your control authority over the true temperature versus the set point. And if you have
Yeah.
a very fast heating system, so very high wattage, but has a bunch of dead time in it, because let's say you have a huge thermal mass, for example, you're going to get overshoot because the amount of time that it takes for the system to
Everything.
respond and notice, and you have to tweak that loop. But I mean, you may have noticed even with an untuned PID loop, you reach your set point and then there's just like,
Yeah, it's just straight.
yeah, it's just,
it, the heater graph looks like this, and then it
yeah,
looks like this. There's no spike and there's no wobble. It's yeah.
yeah,
And what was really cool on the tool changer is I was able to just take out idle temps. They're just zero, because by the time it calls the tool, when the head goes to pick it up, it's hot. Like, it
yeah.
doesn't have time to cool down. It is just
Okay,
hot.
yeah, yeah. I don't actually know what heat up time is,
It's
but
about a
it's
minute from ambient to 255.
yeah, it's more,
I
it's more
I
than
made an
twice as quick.
absurd claim on Twitter, and then people made me fact check it, and it's about a minute. But from like print temp to layer change on like an average multicolor tool changer print, you lose like 10 to 15 degrees, and that's damn near instant.
Yeah, yeah, that
So
that really is. Um,
yeah. But so one of the questions we got from Twitter, and you like kind of segued into it there, was nozzle geometry. So one of the things that came out right at the same time as Revo was the CHT nozzle announcement, which
yeah,
is a licensure of the matchless nozzle, which has been around for a while. But the question was, what do you think the theoretical limits of 1.75 millimeter filament are with nozzle diameter oddities? So we have like CHT that's bringing it up to 1.8 or 2 millimeters with a 1.75 feedstock. What kind of wildness do you think we could achieve um, with something else? I don't know. Right? Yeah, it's an
so
interesting question.
in terms of fundamental limits, I think that if we assume a system with unlimited grip, which is a big assumption, very, very big assumption,
Yes.
you Probably your Euler column buckling limit of the cold polymer when you reach plastic deformation on the cold side due to back pressure and grip. That is probably your limiting factor.
Okay.
Now, I think that's probably unrealistic, but my point is that
We
if
broke
you
Sanjay.
can deal with more back pressure, you
Hmm.
will be able to melt more plastic per second by um, doing funky things with your internal nozzle geometry. Um, Ad absurdum, let us imagine a nozzle that is extremely like so a zero point 0.8 nozzle, but that you have a very very long and capillary. Yeah, no, I think that argument doesn't hold water, but the, you could introduce as many microchannels as you wanted and
Yeah.
really go ham. You would create more back pressure, and you probably the next thing that you bump up against is a grip limit um,
Yeah.
on your
I
extrusion system. Um,
and then that's the manufacturing limit. Like the matchless is and the CHT was made in a way that is like possible. I think to introduce new geometry in there, you have to start doing weird things like centering and stuff that doesn't necessarily lend itself to an efficient or an affordable manufacturing process for something like this.
yeah,
I think about things like through coolant channels on drills, where like the coolant follows the drill flute,
yeah,
and
yeah. Do you know how that's done?
yeah.
Yeah. Um,
Uh, for the people that don't know, a lot of those drills are made straight, and then they're heated and pulled on a mandrel and twisted, or they're centered with a lost process.
Yeah, you take basically like fishing line,
Yeah,
and you twist you take the compacted powder blank and you twerk it like that, and so you end up with like a helical DNA strand, and then you have to like make sure that you grind it in like all in phase.
it's
Um,
wild. There's a reason those drills are like $600 a piece.
yeah. Um, there's also one other weird trick. Um,
If
I
you're gonna
think
make it later, don't say it because I want
I
it.
think that there's a patent that may just have been published of ours, um, and this is going back a ways. Um, but I think it goes to show that we've been thinking about the kind of CHT thing for some time. It's a manufacturing issue more than it is so much a um, design or theoretical understanding. Um,
Hmm.
yes,
Yeah,
it's
if you
been
guys
published
haven't
in
seen how the
France.
CHT nozzles are manufactured, go check out CNC Kitchen's video on when he reviewed them. He's got a nice destructive teardown of them, and
Yeah,
you can see the angles they're drilled at and how that geometry is made,
yeah,
and it's pretty neat.
it's
Um,
yeah, it's nicely done. Can I send you a link on Zencaster? Yeah, there we are.
yeah, there's a chat, and we can add that link to the show notes on all the places we post this. Um,
Yeah,
let's see.
let me see. You need to download the PDF, and if you want the pictures, download the PDF and scroll to the end.
Okay.
I I'm not going to say anything, and I'm interested to hear what you think just by looking at the pictures.
Oh, interesting. I see why you haven't made this.
It's actually quite easy to make, and that's one of the core aspects. Um,
Oh, weird. Okay, so like you are compressing. Can I talk about it? I mean,
yeah,
it's
all right,
it's
it's
published. Okay,
public.
you're compressing and expanding the filament during the melt path in different directions. So you're changing. Interesting. You're almost like creating a shear path in here, aren't you?
So, do you know what Prandtl number is?
No.
Prandtl number is like a dimensionless unit that describes the fluid's propensity to transfer heat, and it is essentially the balance between, or uh, at one extreme you have something like mercury, um,
Mm-hmm.
which is a very conductive fluid, and then at the other extreme you have, well, there's lava, and then second to lava is polymer melts. Um,
Okay.
and so polymer melts, they really don't like for heat to, the heat just really doesn't conduct through them
Right. Yeah.
naturally.
Yeah.
Um, so you have to force the heat around.
Yeah. So in like figure 17, 19, 20, like that one has a really big expansion zone at the end. Like I can almost see how the filament would almost kind of like create an eddy current where like the melt would stay in that expansion path while pushing the solidified down into the nozzle where it would get melted again, and like you would have this like kind of like rolling current. uh it's one of the last
No.
ones.
So
No, okay.
um,
My intuition is wrong.
this one
Excellent.
is, and it's again a bit of an ad absurdum example, but it preserves what you call like equivalent hydraulic diameter down the tube.
Okay.
So any given cross section has an equivalent resistance to flow of some circular diameter. Um, so a and there are known rules of thumb for converting, say, a square tube of 1 by 1.
Mm-hmm.
What is its equivalent resistance to flow compared when described as the equivalent circular cross section? And there are ways to calculate this because as you go towards this more oblong geometry, you end up with more skin friction. So it's not just about maintaining constant cross sectional area. You actually need to do a bit more than that because you're introducing additional like skin friction and viscous drag.
Okay.
So in that design, you maintain constant hydraulic diameter down the tube, so you don't actually get a constriction in flow or where it's most thinned out. You don't actually have a large pressure differential across that most thinned out point.
Okay. That's
Explained badly
intriguing.
enough?
Yeah, you broke my head a little bit. It didn't. Fluid dynamics never is like directly intuitive, right? Especially
No,
with
no.
polymers and melty things. So that's really cool. I never even thought about this. Uh, yeah, we always learn things when we have you on.
And I guess
So
the neat thing about this is there's the potential that it can basically be free to add to a system of certain construction. Um, so if you have some kind of hot end that's based upon a tube,
Mm-hmm.
and the melt zone is within the tube, that you can deform the tube with a die for
Okay.
a singular
Yeah.
upfront cost of one squisher, um, and then you can, for 0 pennies essentially, and maybe a couple seconds cycle time, add in somewhere in a significant performance increase.
Have you guys made any of these? Have you guys actually tested this?
Yeah,
Of course you have. Okay.
yeah.
That's pretty rad. Yeah, I will definitely add this patent link to our show notes. This is really interesting.
I think for the curious out there as to the physics, the pictures are one thing, but the
Mhm.
pictures are quite cryptic as to why the different variations exist. Reading the description, although patents aren't always they're never the nicest reading. I hate damn things.
On purpose. Right, we write them
We did our
vague
best
but
to
descriptive.
actually, describe what we did well.
This is a really long patent. I will I'll actually read this because this is really interesting. But you bringing up this patent, like, it dives into a whole nother rabbit hole that has been discussed on the internet. And just like as a time factor, I've got about
Oh
10
yeah,
more minutes.
my hand time
But
flies.
the a lot of people were not pleased that you were patenting this, and that Slice has been patenting things in the industry. Like, everybody was up in arms about it for a few weeks. Talk more about that. Give me some background, because I definitely understand, and I think giving you some time to talk about it would be useful.
So I think it's very important to understand the wider market context within this, because that's a significant forcing factor in our decision making process around this, because it's not simply around the philosophy of patents, and whether in the abstract there's something there was, because there had been, like, I don't think anyone really does know the full details of what's happened behind the scenes between some other hot end companies,
Mm-hmm.
but if you put yourself in the shoes of a company who has just had patents used against them, and perhaps you are domiciled in a jurisdiction that perhaps gives less than impartial treatment to
Yes. Yeah.
terrestrial applicants and enforcement versus folks from abroad, um, you then have an opportunity to really go wild and start exploiting that advantage to an extent, and then through patent cooperation treaties, pressing that advantage internationally, which becomes very hard to and very expensive. And so, we're standing on the side looking in, and like, there's going to be a really like or we saw potential for a large kind of IP land grab war
Mm.
type situation to take place. And so if you're sitting there on something that is pretty novel, but you can see that other people, soon might be snapping at your heels, or might end up, essentially locking you out of something that you've spent a few years developing.
Mm-hmm.
One of the surefire way to prevent that is to file yourself,
Yeah.
and then there is that is one aspect, but I'm not going to detract from the fact that also a significant part of our motivation is to prevent, I almost don't want to call them competitors. Um, like we all know the types of hot end
Yes.
manufacturer
Yes.
that we're talking about here,
Yeah.
Right.
and
Owners.
that makes for a very painful situation with something like Revo, because it's actually a very difficult to implement just right system, and it goes wrong in insidious ways, as you've experienced. If you don't get it right, and who ends up getting the flack for that? And it's very difficult for folks to understand.
Yeah. So, I mean, in the end, you're protecting yourselves, you're protecting your designs, you're protecting the innovation that you have put time and effort
Yeah,
into.
I think that it's important to understand part of our motivation, a non-trivial part of our motivation is the traditional patent protection for, we believe we've invented something novel, we've poured a
Mhm.
whole bunch of time into it, and we don't think that, we can see a really fair likelihood that we'd end up with a really unviable business afterwards if we didn't go through that protection.
Yeah.
So that standard preventing other folks from just piggybacking on that, it is part of our motivation. It's not going to obfuscate from that. But there was also another very big factor, and that factor is unfortunately still present and driving some future further patenting. And before any patents like these ended up getting published, we want to kind of state our position and say why and what's
Yeah.
going on and be as clear as we can. I think it's one of my biggest frustrations around this, that I can't just sit here and explain to you what we are and aren't protecting in the system and exactly why and how and why we believe that that's valuable, because it's still under examination and we might have to kick that around.
I understand.
This is not a
Very much.
situation that we relish.
Right.
And I think that if the market was only occupied by other good faith actors,
Hmm.
then there wouldn't really be a need for this.
And that's kind of what I think the detractors are insinuating, is everybody's here just trying to, and it's not necessarily the case.
Yeah, and it's a really tough balance to pull.
Yeah.
And
I mean, would you say, in short, watch Silicon Valley and maybe you'll understand?
I've not watched all of that,
Girth matters.
but yes,
There's a
So
really excellent section of the show that goes over exactly what you're talking about, with just
Yeah,
yeah,
people trying to do great things, but unfortunately, stuff happens, and you have
yeah,
to be willing to protect yourself from what others may want to do with that thing that you've created.
yeah,
yeah. I think that to be clear, what we're not trying or can be bothered with or want to do is go down this like very IP heavy, like blocking, broadest portfolio avenue plugging kind of aggressive approach that you often see in the kind of blank check industries a lot, in your kind of
yeah,
aerospace and medical type areas where there are very, very, very large upfront investments, and so people get extremely aggressive about kind of trying to lock down, and abuse
yeah.
is a strong word, but certainly take
Take advantage.
advantage of every angle that they can get in the book.
And that's
Whereas we
not
just
your
want
goal.
to make hot ends and then like develop the hot ends, make the hot ends, sell the hot ends, develop more hot ends. Like that's what I want to do. But
You're a lot like me. You just want to do interesting work, be comfortable, and not have to fight about it.
right, and it's like as per the blog post, it's almost like offensively simple how it's like phrased, but it's like if we don't do this, then there's a really significant chance because we've
Yeah,
spent like everything that we like can getting like this system, this production line built, like multiple beta testing rounds with really significant changes in them, and those beta testing rounds are in the thousands of or high hundreds of units.
it was a lot. It wasn't
Yeah,
like
and
10.
so each one of those hot ends costs you hundreds of bucks just in the manufacturing costs of those low volume run parts. Then you have to like build like it's yeah. Um,
Okay. So
ugh.
thank you for doing all of that. I don't want to cut you off. I have a couple more questions, lightning
Please.
round, and then we have to go.
Yep.
One, uh, where are the Revo parts being made?
In the UK, some are being made in this building, and some like no more than 3 hours away drive.
Nice. Two, what's your favorite tool or
I
process
say,
that
I
you
say
acquire to
parts.
make that
Just to be
happen?
really clear before I get misinterpreted, like you can't buy a fan that's made in the UK. Machined
Right.
parts are all made within 3 hours drive. Um, yes, there
That
are
makes
some other
sense.
parts that are made America, Europe, uh, Japan.
Manufactured parts are made in the UK.
Yeah, yeah.
Yeah.
Fair.
What's your favorite tool or process that you acquired to make that happen?
It's the one that I can speak the least about, which is the system that puts together a Revo nozzle because it's a composite multi-part thing. We built that from scratch. It's a
Yes.
behemoth. It's like encoderized and strain gauged. Every like we store data from every single part. You can like tell it because you're like doing this like metal to metal sealing process, and you've got to like mush the metal together just right. And you also want to control the OAL and a whole bunch of other factors so that it's yeah. Um,
All right.
Okay.
All right.
This isn't the exact question. I'm going to mold it a little bit to my own desires. What keeps you going? What's driving Sanjay right now? This is the last one.
I think the most exciting part is not the technical feats of this. It's when I look around and I see that all the engineers in the building have a little rack that they've, without being prompted or told, have attached to the front of their machine, and it's got 4 or 5 different color coded nozzles on it, and they're changing them in and out all the time without even thinking about it, because we've
Hmm.
made changing nozzles easier than changing filament. So it just becomes part of the how am I going to print this part decision making process fluidly without even having to kind of think about it. And I think that you've experienced that as well.
I have. Absolutely.
It creeps up on you.
Yeah.
This really makes me not want to start building my printer and just wait.
Well, I mean, if you get a Chimera, you'll be good. You'll be good. So like that's the easy part. That's why I've been pushing everybody around us to get Chimeras for the last 8 months. And like, no, trust me, Chimera's the future. Just stop thinking about it and buy that, and then you'll be good.
Fair enough.
Yeah, there's going to be a mounting solution for everyone in almost every situation out there.
Yeah. Well, this was incredible. We have ran right up to my hard stop, and if you want to come back and talk more about any of these things, I would love to have you. It's always about trying to
It's
connect.
always fun.
But
Definitely.
okay, thank you so much for being here, Sanjay. Chris, do you have anything to add?
No, I would love to talk more about some stuff in the future of just like how you guys went through the development process and all that. Just because I'm curious from a outside perspective of just like what that looks like. Mainly because in the same time you guys have been doing all of this time or all this stuff, I've been working with a company that's doing all this for the first time, and it's aggravating to say the least. So I really would love to hear some of like the more day-to-day stuff of like actually how you guys figured all this out, but we could totally save that for another time.
Talk to your customers.
Awesome.
Fair enough.
Go and stand in the room next to them.
That's
Give them the thing.
the honest problem I'm having with this other company. They don't do that, and that's the anyways.
That's
That's
more
how you get it
common than
wrong.
not.
Yeah.
All right, Sanjay, do you have one last thing to add?
No, just that I've missed you, bro. I look forward to seeing you in person. Also, my laptop's
Maybe
running out
Murph.
of battery. But Murph,
Maybe,
whichever Earth you're at
I,
next, I'll be there with bells on it.
yeah. I honestly thought about trying to get to TCT this year because it's just like there's been no travel and there's been no friends for a long time, and I miss
We'll be
you
at
guys.
Full Next in
But
a couple of weeks' time.
where's that at?
Germany.
Ooh. Good
All
food.
right.
Food for thought. Yeah.
I will catch you guys later. Thank you so much for being on. Thanks everybody for listening. Keep making stuff.
Please do.
This is the end of the podcast. Suck it, Aaron.